Okay, good morning, everyone. Chapter 4 today, transient analysis. Okay, this is going to go by fast. All right, so we're going to look at 4 different circuits, the energy transfer phase of the inductor and capacitor. What I want students to do is not take as many notes as you would usually do, because there are 4 circuits, there are some equations and derivations. We don't go too deep into the derivations for non-E major classes. But at the end of the chapter, there is one single equation that applies for the entire chapter. And there's one single equation, and that's it. And this equation only has 3 quantities. One quantity is a standard constant you calculate from the given component values. The other 2 are basically 80% of your solution. Okay, so 90% of the entire problem solving is just understanding what the problem is telling you, extracting the information, and setting up the problem. And that's it. Okay, so as we go along, I will explain the theory, I will explain the concept. But as I said, you can take notes, but don't worry about noting down every single thing that we talk about, because at the end you will see there's only one single equation. Right? So let's get to it. This chapter excuse me, this chapter is also known as transient analysis. The reason for that is because, did I change this here? Okay, the reason for that is because the response of the inductor or capacitor during this energy transfer phase is fleeting. It is transient in nature, because after a certain point in time, the capacitor or the inductor will receive all of the energy that it can store, and the voltage or current will reach a steady state, right? It will reach a point where it is no longer changing with respect to time. And hence it is also known as transient response or transient analysis. So we are going to look at circuits which have only one energy storage device, which is one inductor or one capacitor. The solutions for the voltage and current will be dependent on time, right? Is the energy being transferred in and out of these components. So we are looking at that energy transfer phase. If the energy is flowing into these components, meaning the energy is being received, we say the components are being charged. So energy received, we say it's being charged. If the energy is transferred back into the circuit, we say it's being discharged. Okay, so again, energy being transferred into the components, we say they are being charged. And then energy flowing out, we say they are being discharged. If you have one energy storage device, meaning if you have one inductor or one capacitor, it requires the solution of a first order ordinary differential equation. Because it's a first order differential equation, we say it is a first order circuit. Okay, first order circuit. If you have 2 energy storage devices, requires a second order differential equation, so we say it's a second order circuit, so on and so forth. Most of the circuits can be classified as first order or second order. Okay, we don't look at second order differential equations in 201 unless I have like extra time at the end of the quarter. Okay, that just goes into a whole different analysis. And so we stick with only first order circuits. Now, first order differential equations, I don't know about you, but that's not my idea of a good time. But thankfully, greater minds have come before us. They have derived these equations, they have solved them, so we don't have to worry about solving them. The equation, as I stated previously, is solved for us. We have one standard generic equation, but as an engineer, it's up to us to understand the circuit, extract the information, and then plug in the values into that equation. And that's it. The 2 kinds of responses we study, actually, let's go here. The 2 kinds of responses we study are known as natural and forced. It is not as sinister as the word sounds. Okay. Typically, I like to use step response. Step response. Forced is simply the application of a source. The source is external to the inductor or the capacitor, right? It's not part of the inductor capacitor. So you connect a voltage or current source, and because of the energy that is being supplied by the source, the voltage for the inductor capacitor now changes. So it's forced from an external source. If you think about it, everything that we have done so far, all circuit analysis we have done so far, is all a forced or a step response, right? Resistors, we apply a voltage or current external to the resistor, and we obtain some voltage or current. So if it's externally applied source and it's charging, meaning transferring the energy into the circuit, it's known as a forced or a step response. If it's simply discharging or losing that energy, it is known as a natural response. Okay, natural response. In both cases, the response has an exponential relationship with time. Whether it's charging or whether it is discharging, they always have an exponential relationship with time. So if it's discharging, it will look something like this. This is a discharging waveform. And on the left, you have the charging waveform. This here is a charging for voltage. This here is for current. In both cases, whether it's voltage or whether it's current, it always has an exponential response with time. If it's discharging, again, voltage or current discharging, again, an exponential relationship with time. That doesn't change. Okay. If we look at the charging waveforms, you might have some initial value of the inductor or the capacitor. It could be zero, it could be non-zero. Doesn't really matter. Okay. Again, it could be zero, it could be non-zero, doesn't really matter. It starts receiving the energy from the source, it builds up the energy level. At some point in time, the inductor or the capacitor will receive all the energy that it can store, and the level flattens out. It doesn't change anymore. It is steady, or it has a steady value with respect to time. And that portion is known as the steady state region, also known as the steady state response, because the value of the voltage or current doesn't change with respect to time anymore. It's constant. And the portion we are looking at in chapter 4 is this portion, transient response, where if you look at that curve signifies that at any given point in time, the value of the voltage or current could be something else, could be different. At t equals to 1, t equals to 2, 0.1, 0.2, 2.3, 2.005, any value of t will give you a different value for the voltage or current. Does that make sense to everyone? Right? And so we are going to derive the equations to describe that behavior, the transient behavior. Transient behavior applies to both DC as well as AC. AC is basically a voltage or current that changes with respect to time. So when you apply that kind of voltage or current, also there is a transient response. We are not looking at that just yet. Okay, in this chapter, you're only looking at generic terms, mostly just DC voltage and DC current. Okay. So based on that, we have 4 different kinds of circuits. We have natural response for inductor and capacitor. We have the forced response for inductor and capacitor. Okay. If you note, we have 1R, 1L, and 1R and 1C in these circuits. But the EQ stands for total equivalent inductance or total equivalent capacitance. If at all it is possible to reduce all inductors in the circuit or all capacitors in the circuit down to one single component, one single inductor or capacitor, then we still refer to it as a RL or RC, first order circuit. Even though physically there might be 4, 5, 6, or 10, or even hundreds of inductors or hundreds of capacitors, if at all it is possible to reduce it electrically down to one single component, it is still a first order circuit. So in this case, we have a simple inductor and a simple capacitor connected to a resistor. It is a RL circuit, a first order RL circuit, or a first order RC circuit. Okay. Physically, you could have more than one, but electrically speaking, is just first order circuit. Similarly, if we connect a source, there, it is still a first order RL or first order RC circuit that is being charged. And we need to have a Thevenin or a Norton equivalent. This is charging, and it is showing you the Thevenin equivalent circuit as a voltage source. And here it is charging and it's showing you the Norton equivalent circuit. Okay, Norton equivalent circuit. So you have 4 kinds of circuit, 2 for discharging and 2 for charging. And we'll talk more about Thevenin and Norton equivalents at the end. So let's look at the first circuit. RL, natural response. What I want to point out first is the switch right here at the center. This is the most important piece of information that you need to extract. Sorry, not information. This is the most important piece of the circuit diagram from where you will extract information. Okay. This is a natural response analysis, meaning there is no source connected in the circuit. Okay, no source connected in the circuit. So anytime you see a switch in the circuit, there will always be a time given right next to it. In this case, it says time t equal to 0. It simply means a random point in time at which you're going to begin analyzing your circuit. Okay, this is the point in time where you're going to begin the analysis of your circuit. You should not care, or we do not care of anything that happened in the past, meaning anything that happened before time t was equal to 0. We are not analyzing for the past. We are only analyzing for the future, meaning after time t equals to 0. But we do need to know what happened in the past, so we know what happens at t equal to 0, and we can use that to analyze for the future. Too confusing? All right, let's look at the circuit at t equals to 0. What does it show? At t equals to 0, it tells us that the arrow is going to flip open. If the arrow is going up, meaning the switch is flipping open, what happens, or what happened before it opened? Before the switch was flipped open, meaning time t less than 0, it would have been closed. That's a conclusion that you have to infer from that image. Okay, that's what I meant by saying that 80% of the analysis is simply looking at the problem and understanding what it is telling you. So in this case, excuse me. In this case, what it is telling you is that before time t equal to 0, the switch was closed. Does that make sense to everyone? At time t equal to 0, the switch is flipped open, meaning before time t equal to 0, the switch was closed. If the switch is closed, you take a look at the circuit. Current source IS was connected to the rest of the circuit for a very long period of time. For a very long period of time means inductor had time to reach steady state. A long time simply indicates steady state. That's all it means. At steady state, inductor behaves like a short circuit. If it's a short circuit, all of the current is flowing through the inductor, nothing is flowing through the resistors. You all with me so far? Okay, everything is flowing through the inductor, nothing is flowing through the resistors because it's behaving like a short circuit. Okay, so now at time t equal to 0, the switch flips open. The left side of the circuit gets disconnected, right? The only thing left in the circuit is the inductor and the resistor. No source, hence a natural response circuit. No source. And now the inductor has certain energy, and that energy is beginning to get discharged through that resistor. Make sense? Our job is to find the equation describing those conditions. But we need to know what that initial energy is. Right? The initial moment of our analysis is t equal to 0. So what is the energy stored in that inductor the moment we begin analysis? For that, we have to look into the past. And here's the important concept. We saw t equals to 0, right? There's a concept of t minus and t plus. T minus simply signifies the time right before, meaning in the past. It does not have a specific value. It simply is a random time right before, and plus is right after. Okay, right after. Right after is important because that's the point in time which you're beginning your analysis. Right before will allow you to find the value for the time right after. Here's the important concept. Energy transfer cannot take place instantaneously, right? When the switch is flipped open, the source is disconnected. All of that energy does not drain instantaneously. You cannot snap your fingers and expect all of that energy to go out. Doesn't matter if you have all 5 infinity stones. It's not going to work that way. Current through an inductor cannot change instantaneously. That's the important point you have to remember. Current through an inductor cannot change instantaneously. So if before the switch was flipped, the inductor was connected to the source, it had reached full charge, it had a value that was equal to the source current IS. After the switch is flipped, the circuit changes to this. Even though the circuit is now disconnected from the source, the current cannot change instantaneously. So the value of this current is still IS. And this is the important concept that you have to understand to determine and set up your problem or to set up your solution. Let's take a pause. Think on that. Let me know if you have questions. Any questions? Yes. Yes, that is correct. The moment the switch is opened, the inductor current will still have that IS value. And that allows us to begin analyzing a circuit. So we apply KVL at the top. When we apply KVL at the top, we can simply write inductor voltage plus the resistor voltage should sum up to 0. Again, here's the derivation. This is the derivation, and the equation does not matter. It's not important in the grand scheme of things. Inductor voltage, resistor voltage can be expressed, right? Inductor voltage VL is L di over dt. Resistor voltage expressed using Ohm's law, V equals IR. You have a first order ordinary differential equation. When we solve that equation, we obtain an expression for the current through that inductor at any given point in time. Current I as a function of time is given by I0 into e raised to minus t over tau. Okay, I0 into e raised to minus t over tau. Let's break down this equation. I of t, meaning the inductor current at any given point in time as a function of time, right? I0 is the current in that inductor at the beginning point of your analysis. And this value you obtain by looking at the circuit in the past. Remember what I said, we don't care about what happened in the past. We are not analyzing the past, but we just need to know what that value is so that we can begin our analysis from the present. Okay, so I0 is the initial value in that inductor when we begin our analysis. This is a discharging problem, so I0 is probably at a certainly high level, and that from that point on, it is simply going down. And that is noted or given by e raised to minus t over tau. It has an exponential relationship with time. T is the variable. Remember, I of t is a function of time. And tau is the time constant. It is fixed, depends on the value of the inductor and the resistor. It's the size of the container, the fluid flow, and the size of the pipe. How fast the energy transfer takes place. Again, so it's the size of the container, meaning it depends on the size of the inductor and the resistor. It's always fixed for a particular circuit, L over R. Whether it's charging or discharging, that tau doesn't change. It's fixed. So as I said, you have a standard equation. Your job is to simply find the values of the components and plug into this equation. That's it. Tau is the easiest because the values would be given to you. You have like a 10 millihenry inductor and a 1000 ohm resistor. Tau is a simple calculation. What is important is determining I0. For that, you'd have to redraw the circuit, set up the problem, and then infer or conclude what I0 value is. And then you plug it into the equation. That's it. Yes. As in this case, I0 is IS. Yes. It'll be different for every circuit. I0 is sometimes also referred to as I, subscript I. 0 or I means the same thing. Okay, 0 stands for time t equal to 0. Time t equal to 0, meaning when you begin your analysis, and I stands for initial. So if you come across or you read the words VI, II, they mean exactly the same thing as V0 or I0. Initial, the point in time when you begin your analysis. Initial values. If it's in discharging, yes, initial value is basically the source or whatever applied current or voltage was. Okay. Once you have this current equation, you can determine the voltage from Ohm's law. You have I of t. You can find V of t simply by multiplying with the resistance R. Power is V times I. You plug into the equation, it's I squared times R. So again, I squared times R. And the total energy dissipated in the resistor has to equal the total energy that was stored in that inductor. Eventually, of course, it goes to 0. So total energy is half Li squared. Same equation we saw in chapter 3. No difference. Okay, same equation. All right, any questions? Okay, let's look at the discharge of a capacitor then. Similar circuit, except the switch configuration is a little different. You have two positions for the switch, A and B. At time t equal to 0, switch flips to B. That's when we begin our analysis. When it switches to B, we can see the circuit changes into simply a R and a C circuit, no source. So it's a natural response. It's a discharging circuit. It's a discharging circuit, but we need to know what the voltage across that capacitor is. For that, we have to look into the past, meaning before the switch was flipped. And before the switch was flipped, it was at position A, where the capacitor is connected to the voltage source, VG. G simply stands for generator, so it doesn't really, that acronym or the subscript notation doesn't make a difference. Whatever the voltage source is, was connected to the capacitor. The capacitor was connected for a long period of time, meaning it has reached steady state in the past. Voltage VC equals VG. When the switch is flipped, the capacitor voltage is still VG, because similar to a inductor, the voltage across the capacitor cannot change instantaneously. Okay, the voltage across the capacitor cannot change instantaneously. So the moment in time when it gets disconnected from the source, the capacitor voltage is still equal to that source voltage. And that allows us to set up our initial conditions. So we can write voltage V0 equals to VG. Then we analyze the circuit, we apply KCL. Apply KCL, we get IC plus IR equals to 0. Ignore the signs. Plug in the equation, we get C dV over dt for the capacitor current. And we got V over R for your resistor current. We solve that first order differential equation, and the solution is exactly the same as what we obtained for the inductor. Exactly the same, no change, no difference. Okay, no difference. V of t is V0 into e raised to minus t over tau. The only change is the time constant. For a RC circuit, the time constant is RC. That's it. No change. It's a product of the resistor and the capacitor. Other than that, the exact same expression. V0 in this case is the maximum charge across the capacitor, which is then diminishing or decreasing. And that's why I said one equation to rule them all, because all the equations have a very similar structure. Once you have the voltage equation V of t, apply Ohm's law and you can find I. I is V over R, power is V square over R. The total energy lost in the resistor is half CV square. Exactly the same as we saw in chapter 3. All right, let's take a pause. Let me know if you have any questions. Yes. Half Li square. Same as chapter 3. That doesn't change. Yes. Mm-hmm. Yeah. It does. That's why we have the time constant, R times C. That simply slows the rate. Basically, if R is smaller, then current is higher, so it charges faster. If R is big, then it takes longer to charge, current is slower. Yes. Yep. When it finishes charging, it acts like an open circuit. So again, yeah, R does have an effect. Okay, then let's look at the step response. Don't worry about the summary slide. We'll summarize this again at the end. Step response for RL and then step response for RC. Simple circuit, you have a source. That source is connected to the inductor or to the capacitor. This time, when you apply KVL, you have VL plus VR equal to the source, VS, not equal to 0. You solve that equation and you obtain I of t is IF plus I0 minus IF into e raised to minus t over tau. Similar structure, similar form, it still has an exponential relationship with time. That does not change. We have one extra term in here. It's not just the initial, but it's also the final value. It's also the final value. There is a reason we don't have the final value in the discharging or the natural response. And again, I will point that out when we get to that one equation. If there is no charge already stored in that inductor, then I0 is equal to 0. It's fully discharged, right? Now you're applying a source, so it's starting from 0 and is going to some value. So it's initial and then final, right? Initial value, if it's completely discharged, meaning it's 0, then you only have to worry about the final value. So then the equation simply becomes IF minus IF into E raised to minus T over tau. Okay. Tau time constant still remains the same, L over R. RL circuits, it remains the same, it doesn't change. For a capacitor, same procedure. You have a voltage source connected to a capacitor. You go through and apply KCL. This time IC plus IR is equal to the source IS, not equal to 0. So this time you have a first order differential equation which you solve and you obtain V of t is Vf plus V0 minus Vf e raised to minus t over tau. Again, exactly the same form, same structure, no difference. It also, again, has the exponential relationship with time. So inductor, capacitor, charging, discharging. It's always e raised to minus t over tau. Tau is the thing that changes. For a inductor, it's L over R. For a capacitor, it's R times C. It doesn't really matter whether it's charging or discharging. Always, always, always has the same structure and same form. And here is our grand equation. One equation to rule them all. X of t is xf plus x0 minus xf into e raised to minus t over tau. Let's break it down. Starting from the bottom, there are three quantities here: xf, x0, and tau. Tau is standard. For RL, tau is L over R. For RC circuits, tau is the product of R and C. Doesn't change. Okay? So it doesn't change whether it's charging, doesn't matter whether it's discharging. 0 or I signifies the initial value. F is the final value. Here's the thing. If you're talking about a natural response circuit, discharging, what is the final value? 0, right? Always is 0. It always is 0. So for discharging or natural response circuits, final value is always 0. Hence, if you plug in xf in this equation, what do you get? X of t is x0 times e raised to minus t over tau, which is what you obtain for the natural response circuits. Right? Exact same equation. And hence, those equations didn't have xf in it, because when you're analyzing for a natural response circuits, it is always equal to 0. xf is always 0. It doesn't matter if your component gets interrupted while it is discharging. So for E major classes, we do examples where there's multiple levels of switching. Okay, so a inductor capacitor may start discharging, it's going towards 0, but before it can reach 0, an external source is applied and it begins charging again. So it never has time to reach 0. If you're taking the lab, you will see that next week. Your capacitor will begin discharging, but it doesn't have time enough to reach 0, and it begins charging again. But when you're analyzing just that portion, just that discharging portion, you still enter XF as 0. It doesn't matter whether it's not going to reach 0, but you still use XF as 0. It's very important. Again, for non-E major classes, I will not give you those kind of problems, but it's still a concept as an engineer you should realize, you should understand. Okay. And that's why the equation for the natural response does not contain XF, because XF is always 0. For everything else, you have a value for XF, you always have a value for X0. So your job as an engineer is to understand the circuit conditions, extract as much information as you can, determine the value for X0 and XF, and then directly plug it into these equations. I mean, into this equation and write down the solution. That's it. That's all you have to do. So again, 80 to 90% of the solution for this is simply finding or determining the information for X0 and XF. That's all you have to do. All right, let's take a pause. Let me know if you have any questions. Any questions at all? Okay. All right, then let's look at the first point, which says find the equivalent circuit. Okay, for that, I'm going to illustrate using a random example. So I have a circuit with a resistor R1, capacitor C, voltage source Vs. What is the voltage that is being applied to this capacitor? Not that difficult a question. Vs, yeah, the answer is Vs. The resistor in the middle doesn't matter because the resistor is just a current controlling component. Eventually, the voltage across the capacitor will reach Vs. So Vc in this case is Vs, meaning XF, my final value, should equal Vs. Excuse me. Initial conditions, of course, if the capacitor is fully discharged, we just say it's 0. Final value is Vs, voltage source Vs. How about for this circuit? You have a capacitor, you have a voltage source, Vs, R1, R2. Is Vs still being applied directly to the capacitor? No, it's not, because it's going through R1 and R2. If I redraw the circuit in a way that makes a little bit more sense, the circuit actually looks like this. Capacitor C is in parallel with R2. And that parallel combination is in series with R1. If the capacitor C was not there, what happens to the voltage Vs? It splits between R1 and R2. Right? When is the capacitor not present in the circuit? When it behaves like an open circuit, which is when it reaches full charge. That charge voltage will be equal to the resistor voltage R2 because they're in parallel. So that's another way of looking at it. Okay. So it reaches full charge, becomes like an open circuit. Everything flows through those resistors. Voltage is divided across R1 and R2. So Vs is not being applied directly to that capacitor. In order to find the voltage for that, we have to find the Thevenin equivalent circuit as seen by that capacitor. We have to remove the capacitor from the circuit and analyze the rest of the circuit to determine the voltage between the terminals A and B, or where the capacitor was connected. You have to reduce it and find VTH. And then VTH would be the voltage across that capacitor or the final voltage. For this non-E measure class, I'm not going to give you like a large circuit, analyze it for Thevenin and Norton, and then, that's not what I will do in example problems. But it's an important concept that students should understand. This is also a perfect example of why we need to study Thevenin and Norton and why it's so important for circuit analysis. Okay. Anytime you perform an analysis, there are multiple components. We have to reduce it down to one single component. And we do that by applying Thevenin and Norton analysis. Does that make sense to everyone? Right. So if the voltage source is connected directly, whether it's a voltage or current source connected directly to the inductor and capacitor, then that final value can be taken directly from there. If not, we have to find the equivalent circuit. And that's why I have it as step number 1. So again, 80 to 90% of the solution is simply determining the right values for XF and X0. Questions? Any questions at all? Okay. 2 more slides. Let's look at what happens when you plot these. Exponential relationship. The value of the inductor does not matter. The value of the capacitor does not matter. The value of the resistor does not matter. The value of the source or the energy does not matter. That will only change the level. The relationship always, always, always stays exponential. This is for charging. And this is for discharging. All equations had e raised to minus t over tau always have an exponential relationship. That does not change. There's always e raised to minus t over tau. When you plot, sorry, not plot. When you use that equation, you can plug in any value of t. T is equal to 5, t is equal to 0.1, 0.02, 0.0005. Doesn't really matter what value of t you put in, that equation is valid for all points in time greater than t equal to 0. Okay. If we plot in t equals as a multiple of tau, 1 tau, 2 tau, 3 tau, and so on and so forth, we get exact values at every time constant interval. Mathematically, if you put in t equals 1 million seconds, you would still obtain some numerical value. It'll be very, very small, 0.00000 something, but you would still obtain a value. It will never be exactly equal to 0. So when do we put an end to it? We put an end to it after 5 time constants. After 5 time constants, the value of the energy either exceeds 99% or is less than 1%. So if it's charging, it acquires more than 99% of its value after 5 time constants. Or if it's discharging, it loses more than 99% of its stored energy. So after 5 time constants, we say that it is either fully charged or discharged. Okay, and this is standard accepted convention. This is standard accepted practice in electrical engineering. After 5 time constants, we put an end to it. We say it's either full charge or full discharge. Mathematically, it does not matter. You could put in 1 million time constants and you would still obtain an answer. If you look at these numbers, after the first time constant, we're going to look at the chart. Right here is the first time constant where it's charging. It acquires more than 60% of its total value right after the first time constant. It's a big jump, right? It's exponential. So there's a big jump and then it flattens out over time. Similarly, when it's discharging, it loses more than 60% of its value after the first time constant. It's a big drop and then it flattens out as close to zero as possible. Okay, so in both cases, whether it's charging or discharging, it acquires or loses more than 60% of its stored energy, or acquires more than 60% of the energy after just one time constant. That's how we have to read this chart. But again, the value of the components and the value of the source does not matter. It always follows this exponential nature. All right, any questions? As I said, the theory and the concept is simply that you're charging or discharging, energy is being transferred in and out. We are just looking at the voltage and current equations for the charging and discharging portion, but it's one single equation that applies to everything. You don't have to worry about anything else. We'll end class here today. That's the end of the explanations. We'll look at example problems in the next class on Monday. Quiz on Monday on chapter 3, not the entire chapter. I'm letting you know right now, it's going to be piecewise linear analysis, one problem. There are example problems that are solved. It's been there on the Canvas website in the beginning of the quarter. So please look at that PDF. It's on the slides webpage. Download that, go through the example problem. Let me know if you have any questions. Also study the example problems that I did in class and the homework also. And then reach out to me if you have any issues or any questions. Otherwise, I'll bid you a good day and I'll see you all on Monday. Have a good weekend.